So now that we've seen some of the graphs, we can jump right into section 8.3, which deals with polar graphs of complex numbers. So if I start with a complex number, say a plus bi, I can graph this in rectangular coordinates by looking at the two axes, one as real and another as, spelled horribly wrong, imaginary. Complex, there, shorter. So if a is some real number, b, remember the coefficient on I is always another real number. There's the point, a plus bi, which is why you sometimes see complex numbers represented as an ordered pair. Now, I could, if I wanted to, determine that distance, right? I could use the Pythagorean theorem, and I could determine that distance. But what works is that I can also use this to realize these things in terms of this angle theta. I know, based on our definition of sine and cosine, that, let's call this guy z. This distance along the blue line here is called the absolute value of z, or sometimes the modulus. And that distance is going to be equal to the square root of a squared plus b squared. Just comes directly from our Pythagorean theorem. But what's also kind of nice is that a is equal to the modulus of z times cosine of theta, and b is equal to the modulus of z times sine theta. That follows directly from our definition of sine and cosine and our expansion of a unit circle into a circle of arbitrary radius. We proved that stuff earlier in the semester. But then I could rewrite these as z equals modulus of z cosine of theta plus the modulus of z sine of theta times I. You'll see this written sometimes too with the I out on the other side and the modulus factored out. Cosine of theta plus I sine of theta. And then we've got two different components. The modulus, which we already defined, and then this theta, the angle that we needed to move through to get up to the line connecting this complex number point to the origin, is called the argument. So if I wanted to start with a complex number, like -1 plus root 3i, and I wanted to write this in its polar form, call it z. I can find the modulus of z, and that's going to be square root of -1 squared plus root 3 squared, square root of 1 plus 3, so that's going to be 2. If you go ahead and use the fact that 2 cosine theta equals -1, and 2 sine theta equals square root of 3, you come up with theta equals 2 pi over 3. So z is equal to 2, it's its modulus, times cosine 2 pi over 3 plus I sine 2 pi over 3. We can convert it into that form. Now, you might ask yourself at this point, why would we possibly want to? And the answer is, it really can be helpful with arithmetic. So, if I have Z1, R1, where I'll let this R1 just be something to represent the modulus of this Z1, so I don't have to write it over and over again. Cosine of some theta plus I sine of that same theta. And Z2, R2, cosine theta 2 plus I times sine of theta 2. If I want Z1 times Z2, I always thought this was really cool. If you multiply the whole things out, multiply both these things out, distribute here, multiply it all together longhand, factor everything back out, this is what you come up with. All we did, we multiplied the two arguments together, or multiplied the moduli rather, added the arguments. Whole thing falls right out. Now multiplication, you might say, well, that wasn't so bad when I did it in pre-calc. Okay, well, let's divide these two. And rather than having to go through and find the conjugate of the denominator and multiply both sides by it and then cancel everything out where it goes, divide the moduli, subtract the arguments. So, what I'm really looking at, geometrically, if I have 2 points, say, here's Z1, and here's Z2, some theta 1, R1, theta 2, R2. To find out where they're multiplied, I'm rotating by this much, and then I'm rotating by this much. So I'm probably going to end up somewhere over here, and I'm going to take this length and multiply it by this length. So there's a nice geometry that's actually underlying the way the arithmetic works for these things. The division works the same way. I'll give you a practical example. Let's suppose that Z1 equals 2 times cosine of pi over 4 plus I times sine of pi over 4, and Z2 equals 5 cosine pi over 3 plus I sine pi over 3. So probably found these things geometrically. And if I want to take Z1 times Z2, well, I just multiply the moduli together. So I get a 10. And the cosine, pi over 4 plus pi over 3. Let's see, that'd be 3 pi over 12 and 4 pi over 12. So cosine 7 pi over 12 plus I times sine. 7 pi over 12. And similarly, if I took Z1 and I divided that by Z2, I'm going to get 2/5 as my modulus. The cosine, if I take pi over 4 and I subtract pi over 3, I get negative pi over 12 plus I times the sine. Negative pi over 12. So, as we move forward with these things, and especially when you see these sorts of problems in calculus class, it's, I think, easier to deal with these things and these complex numbers by treating them in their polar form, especially when it comes down to the arithmetic, and like we saw on the last page, that geometric interpretation can really help.